values. Yes?
42.
42? Okay. 42 for 8.2. All right, so we have the region bounded by, this is 42. F of x equals ln x, and y equals 1. And the coordinate axis is revolved around the x-axis. So they also say that x equals 0 and y equals 0. It's in there. Those are the coordinate axes. So let's see, let's try to draw a picture. So y equals ln of x looks sort of like this, where this is 1. Okay, so that's my y equals ln of x. Y equals 1 would be that line. Y equals 0, of course, is this line. And then x equals 0 is this line. So the one that's bordered by all 4 is right here. That's my region, correct? And then it says, please spin that around the x-axis. Okay, so if we spun that, we could create that shape. And then it kind of like does something like this, right? It's kind of hollowed out on that side. Okay, so we have a feel for what this thing looks like. Let's set this up. I have to figure out, do I want this to be a shell method, or do I want this to be like a disk method, washer method? Yeah. I think shell's much better, because if I cut this way, I have to change, right? I have to change from here to here. But if I go shell method and I cut this way to make shells, then I just have a top function and a bottom function. That seems good. So let's do the shell method. So we want a volume is equal to integral. This is cutting the y-axis, so it's all going to be y stuff. So I'm going from 0 to 1 of 2 pi r, which in this case is y. And then I get h, which is the top function minus the bottom function, but it needs to be in terms of y. This function, y equals ln x, is the same as x equals what? What was that? E to the y. Very good. It's e to the y. So this is x equals e to the y. This is x equals 0. So I just put in here as the height is e to the y, or e to the y minus 0. But I think that that's going to get the job done. dy. And now we get to the part where, did you get this far? Okay, good. And so now we need to use integration by parts, correct? The 2 pi can come out of the integral, so we don't have to worry about it. So I could just write this as 2 pi integral of y e to the y dy. Okay, and so now we're ready for integration by parts. So we need to set up a u and we need to set up a dv. And so what I'll do is I'll say, let's let u be y, and let's let dv be e to the y dy. Now, I could have done it the other way. I could because I know the derivative of both, right? I can take the derivative and the antiderivative of both sides. If you watch through all my videos on this, I'm sure I said this. And that is that we want to put the thing here that when I take the derivative, it gets simpler. So if I take the derivative of y, I get 1. If I take the antiderivative of y, I get y squared over 2. I don't want to make my life more complicated. I want to make it less complicated. So it makes sense to let the y go here, not over here. Does that make sense? So I want to take its derivative, not its antiderivative. Okay, that's important. So du is equal to 1 dy. And then v is the antiderivative of e to the y, but that's just e to the y. Okay, so now the equation goes that I'm going to rewrite this. The 2 pi just stays there. I guess I still have 0 to 1. And then I'm going to replace it with integral of, oh, sorry, just a second. Parentheses would be more like it. So parentheses, I have u times v, which is y e to the y e to the y. But then that's going to be evaluated from 0 to 1 because that got taken outside of the integral. Minus the integral from 0 to 1 of v du. So the v is e to the y, the du is dy. So I have e to the y dy, and that's it. Okay, now let's keep going. This is 2 pi. If I plug this in, if I plug in 1, I get 1 e to the 1, which is just e. And then if I plug in 0, I get 0 times e to the 0, but 0 times anything is just 0. So it's just e. Then if I take the antiderivative of e to the y, it's just e to the y, evaluated from 0 to 1. Okay, so this is equal to 2 pi times e minus, if I plug in 1, I get e. If I plug in 0, what do I get? 1. So I get minus, parentheses, e minus 1, which is, still have 2 pi. I get e minus e, which is 0. And then, so the e's kind of cancel. And then I have minus minus 1, which is just 1. So this is just 2 pi. Does that make sense?
Yes.
Okay.
For when you did y e to the y and then evaluated at 0 to 1.
Yes.
Could you take that and say y e to the y minus and then solve the integral and then evaluate the whole thing from 0 to 1? Or do you have to evaluate the first part from 0 to 1 and then minus?
Yeah, you can. You can do that. So you could say before you evaluate from 0 to 1, first take this antiderivative and then do the whole thing from 0 to 1.
Yeah.
But just be careful because it's really easy to mess up like one parentheses and it all falls apart. And especially with this minus sign right here that you have to be careful of. So the easy answer is yes, but be careful doing it. And so I would probably do it this way just to make sure that I didn't mess up my parentheses. But yeah, it will work. Other questions? Yes, sir.
We needed 31.
31, sure. Okay, 31, we have integral of e to the 3x, e to the 3x, sine of e to the x dx, sine e to the x dx. All right. This one seems in some ways to be sort of a pain because of the e to the x's. So, but the thing is, if we really wanted to, we could get rid of the e to the x's. And the way that we could get rid of them is to use substitute for the e to the x to just like have it go away. Now, do you have to do that? No, You probably could leave it in and you might be able to work it out that way anyway, but I see it will work. So we might as well give it a try. So what I want to do is I'll say, since we're going to use U and V in the integration by parts eventually, I'll just use W. So let's let W be e to the x. So dW would be e to the x dx. So I need one of these. Oh, by the way, this e to the 3x, does everybody agree that that's the same as e to the x cubed? So I could write this just to be very clear what's going on here. I've got e, this is e to the x quantity cubed, right? Or another way of thinking about it is it's e to the x squared times e to the x times sine of e to the x dx. And the reason that I write two of them by themselves and one by itself is I need one of them to go with the dx to make this substitution. So I wrote it out by himself, and then I have two of them that I'm actually going to substitute in a w. So this becomes w squared sine w dw. Is everybody with me on that? Okay. So now this looks more reasonable in a sense than it did before with all the e's in there. So now we will go ahead and do integration by parts. We need a u and we need a dv. Suggestions?
What happened to the e that was in the middle?
This one.
Yeah, where'd it go?
Yeah, good question. So to get a dw, I need to have an e to the x dx. So all of that, which is here and that, became that. Make sense? Perfect. Okay, so what should be u? Yes, sir.
I think that w squared should be u because you will be able to make it simpler by taking the derivative. And
Exactly.
If you sine, you're just going to go in a loop.
That's right. And so we want to make things simpler. This thing will get simpler if I take its derivative. So let's put this as u. So that's w squared. That means that my dv is sine w. So du is equal to 2w dw. And this was dw also. I'm trying to save space, but it didn't work. And then v is, let's see, so I need an antiderivative of sine. So whose derivative is sine? Negative cosine. That's right. So negative cosine of w. Okay, now we can use integration by parts on this thing. So let's go up here. And we can rewrite this as u times v. So this is negative w squared cosine of w minus, so minus the integral of v du. So the integral of v, which is negative cosine of w. By the way, so it's going to be negative, right? Negative cosine of w times 2w dw is negative. So if I wanted to, I could just put it in here as positive and make that positive. Is that too much? I always hesitate to do multiple steps at the same time, but it definitely is going to come out negative. And so I could pull that negative out and make that a positive. And then I get 2w cosine w dw. But how do I do that integral? Integration by parts. Exactly right. So we need to do integration by parts on this thing again. So I get a u, and in the same way that we did it before. I'll make it 2w, and then the dv could be cosine w dw, and then du is going to be 2 dw, and v will be whose derivative is cosine? Sine, yep. So this is sine w. All right, so now we can rewrite this thing using this integration by parts. The negative w squared cosine w just is hanging out, plus, okay, and I say parentheses, and that's really important usually. Plus makes it a little less concerning, but make sure to put parentheses in when you have to do this more than once, just to not mess up your signs. And then you have u times v, so 2w sine w, 2w sine w minus integral of v du. So I get 2 sine w dw, 2 sine w dw, close parenthesis. All right, but that one I can do. So that's an integral that I know the antiderivative of. So let's just plug it in. I still have negative w squared cosine w plus 2w sine w. And then I get minus, what's the antiderivative of sine? So negative cosine. So I have a negative cosine. So that's positive 2 cosine w plus c. But we didn't start with w's, so we probably shouldn't end with w's. What was w? W is e to the x. So now just substitute back in e to the x for all the w's, and we're done. So we can just say that, so the answer is negative e to the x quantity squared cosine e to the x plus 2 e to the x sine e to the x plus 2 cosine e to the x plus c. And that's it. Questions on this one? Everybody good? Okay. Any others to look at? Yes.
I got a bit confused just looking at number 7.
7. Let me look. Okay. Use a substitution. Yep. Then evaluate the resulting integral using the formula for integral of ln of x dx. Yes. I hate the formula, but okay. We'll do it anyway. All right. So 7, we have integral of secant squared x times ln of its like tangent x, is it plus 2? Plus 2 dx, is that it? Okay, so let me help you to get it to the integral of ln of x, and then we'll talk about that for a minute. The first thing that I could do is I could just u substitute or w substitute or whatever letter you like for that whole thing. Okay, if I do that, so let's say I say that w is equal to tan x plus 2, then dw is going to be equal to secant squared x dx. So now all of that secant squared of x and dx, that's all going to turn into dw. And what I'll be left with is integral of ln of w dw. So now if we know the integral for this, then this becomes pretty trivial. And I'm guessing from what they said that they gave you that integral. It's not, yeah, they did. It's just on the page before. Integral of ln of x dx is x ln x minus x plus c. By the way, where did that come from? Well, integration by parts. Because all you'd have to do, if you wanted to actually do this integral without knowing that formula, let this be u, let this be dv, do integration by parts, and this comes out exactly. Okay, so this isn't even very hard. But they said use the formula, so we will obey. X ln x minus x plus c. So w ln w minus w plus c, I believe is correct. Yes. Okay, so this is the antiderivative, and you could get that just using integration by parts. And then we need to get rid of the w's. But w is tan x plus 2. So we could just rewrite this as w is tan x plus 2. Ln of w, so times ln of tan x plus 2 minus w, so minus tan x plus 2 plus c. That's it. Make sense? Cool. What else? Yeah.
Can I ask how to include it by parts?
Sure.
Got it dw?
The integral of ln x dx, for sure. Let's just use integral of ln, let's do it this way. Ln x dx, correct?
Yeah.
So this is a great example actually, because like, I don't know, I mean, I guess I just told you right here, but it's like, if I look at that, it's kind of like, so do I know anything whose derivative is ln of x? And the answer is absolutely not. I do not know the answer to that. But what I can say is I'm like, but wait, I do know the derivative of ln of x.
Yeah.
And maybe that could help me. And so what I say is like, okay, yeah, I know the derivative of ln of x, correct? And I know the antiderivative of, well, 1. So now if what's du? It would be 1 over x dx, correct? And then v, the antiderivative of 1 is just x, correct? Okay, so now I could say that this should be u times v, so x times ln of x, minus the integral of v times du. So v is x, du is 1 over x dx. So together that's just dx. Because x times 1 over x is 1. Now I could just take an antiderivative of that, and I get x ln x minus antiderivative of 1 is x plus c. And that's it. And that's what they said to plug in for. So see, that's not even really that hard. But you do have to know to use integration by parts. Other questions? Yeah. 40. Have you watched the some of the examples on this section? Hopefully so. One of the ones that's really cool is when you have like e to the x and cosine. If everybody's watched that example. If you haven't watched that one, watch it. I don't want to do it right this minute, but because it's online, but watch the one for sure that is the integral of e to the x times, like, I think it's cosine of x dx.
I think cosine or dx.
Yeah, something like that. And it's super interesting. And maybe this is one like it. I don't know. No, it is not. Okay, so we have the integral of e to the square root of x dx. Interesting. Okay. Is that the whole thing? Yes. Okay. Well, this is interesting because it's like, well, do I actually know how to do this? I don't know an antiderivative for that off the top of my head. There's a couple ways that I can think of to maybe like play with this. I don't know if any of them are amazing. Well, actually, some of them are. So there's a couple ways that I can think of going about this. One of them is right. Maybe both of them are right. And first one is, I don't know the antiderivative, but I do know the derivative. Right, so I could just say, let's let this be u, let's let this be dv, and let's see what happens. That's one way. The second way would be, let's be very clever. Okay, so what I mean by that is, I'll show you the clever way, and then we can decide which way we want to go. So the clever thing I could do is I could say, this is actually the same thing as e to the x divided by e to the square root of x. Is that even true? No, it's not true. I don't think it's true. So I don't think this is going to work. It'd be better if it were true. No, I don't like it. Okay, so that's not it. So forget two ways. We're back to one way, and I think that one way is good. Okay, so I'll let u be equal to the thing that I know how to take the derivative of, right? Which is, in this case, e to the square root x. Then dv is equal to everything else, which in this case is just dx. So du is the derivative of that. So the way that I take the derivative of e to a power is it's e to that power times the derivative of the power. Well, that's x to the 1/2. The derivative of x to the 1/2, I suppose, is 1/2 x to the negative 1/2. So this is 1/2 x to the negative 1/2 e to the square root of x. Okay, I could clean that up a little if I wanted to, but v is equal to x. All right. Now, let's rewrite, and hopefully we've made our lives better. So first we have, it's u times v. So I get x e to the square root x. X e to the square root of x minus the integral of v times du. V times du, I get 1/2. I'm just going to put the 1/2 outside. I could put it inside too, either way. And then I get x times x to the negative 1/2. But that's what? X to the positive 1/2, correct? So I get x to the 1/2. If you like, it's the square root of x. Right, x to the 1/2. Times e to the square root of x. Times e to the square root of x dx. Okay, and then the question is this any better than what I had before?
Well, can't have you got any potential?
Yeah, that's the question, is do I know an antiderivative of that?
Because if you do the reverse chain derivative, or like not chain, is it chainable? It's like you take e to the x, e to the square root of x, and then you take the derivative of that. That's yeah, okay, that doesn't work.
Yeah, it's not amazing, right? So the question is this going to be helpful to keep going? Maybe. So we should probably try it. Okay, so this is a good problem because it's like already I'm kind of like, well, I am kind of like, I'm not sure that doing all this work is going to get us the answer. I'm kind of like, it might. So let's try it. And this is kind of how these types of problems go, is you try some stuff and it might work. Let's see on this one. I'm going to let u be equal to the square root of x. Well, okay, just say. This is interesting. So everything that I know tells me to leave it the same. If you use this the first time, use it the second time. Don't change it back the other way, because a lot of the times that undoes the work that you did. So if this was you the first time, you probably want that to be you the second time. So let's do it and just trust. And then that means that dv would be square root of x dx, saying that du is equal to, okay, well, we already did this. It's 1/2 ex to the negative 1/2 times e to the square root of x dx. I didn't even write that over here, did I? dx. And then v is equal to, okay, I need to take the antiderivative of x to the 1/2. So I bump the power up to 3/2 and I divide by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So I get 2/3 x to the 3/2. Is everybody a believer? Everybody good with this? Okay, then we're going to rewrite. See what happens. So this is e to the x, e to the square root x. That just hangs out. Then I get minus 1/2. And then I'm going to replace this integral with a bunch of stuff. So I need to open a parenthesis. And I get u times v. So u times v is 2/3 x to the 3/2 times e to the square root of x. Okay, minus integral of v times du. All right, so I get an x to the 3/2, and I multiply it by an x to the negative 1/2, which gives me an x to the 2/2. Question?
Yeah, I just remember learning about like the tabular method.
Yes.
I was wondering if that would work on this type of problem.
Yes, it would work. So I don't teach that because it's just a way of kind of doing the same thing in some sense. But if you like it, use it. I don't necessarily like endorse it per se as the way that I would like you to learn it, but it works for sure.
It wouldn't work like any better on this one. You don't think?
I don't know that it would necessarily. It might. I don't know. But let's keep going. So we've got x to the 3/2 times x to the negative 1/2, which is x to the 2/2, which is otherwise known as x, right? So we get 2/3 times 1/2 is 1/3. So I get 1/3. I'm going to write that on the outside. So 1/3 x times e to the square root of x dx. Huh. Interesting. Okay. This is for real? Okay, just a second. I'm thinking. So we had a square root show up, and we had an x show up. That is not better. Huh. Makes me think that I'm doing it wrong. See, what I really wanted to happen is I wanted this to end up being basically the same thing as this. That would have been very, very good. If I missed something. This is true. Huh. I just have a feel, I mean, I could do it again, but I have a feeling that it's just going to get worse. Huh, okay. Yes,
I'm not sure if this would work,
okay,
but in the beginning equation,
yes,
if you, well, I don't know if this is correct, if you substitute like u or like u substitution for
Yeah.
square root of x,
uh-huh,
and that becomes 1/2 square root of x dx
yes,
du, and then you times the 2 square root of x du, and then you substitute that in, and you'll have like 2 square root of x e to du, and you can substitute the square root of x.
just a second, okay.
Yeah.
So you just said, make a u substitution for the square root of x.
Yes.
Okay, so you said this is square root of x, and then du is equal to 1/2 x to the negative 1/2
dx, and then
dx. I agree with you.
And then you times that, the 1/2 x negative 1/2 over to the du side. And it becomes 2 square root of x du, which isn't the same variable, but you can substitute the square root of x again for u. And it becomes 2u du.
So you're saying to move this over?
Yes,
Okay, I hear what you're saying. So you're saying make dx. This isn't something that I would expect out of a problem, but I hear what you're saying. So you're saying that you could write this as 2 square root of x
du.
du. This is really, really, really bad. You don't really want x's and u's to mix.
Yes. But then you can substitute the square root of x for u. Because I don't know if you can.
Okay, let me try something that I think is what you're getting at.
Wait, could you have something you though, like instead of writing that as square root of x du?
Okay, so the problem is you can only substitute this in for u if you have this sitting there, which we don't, but maybe we could. And this actually is pretty close to what I was trying to do at first. I just was thinking about it wrong. I'm not even sure it's going to work, but let's try it. So what I could do is I could say that this is the square root of x over the square root of x. Certainly that's true. Everybody agree? And then I could say I have a 1/2 in here and a 2 out here. Does everybody hate me right now? After doing all of this and now we're going back. This is actually a great problem because it shows that like these aren't easy. Like you have to, sometimes you just go down the wrong path and it's like, well, that's a bummer. It's okay. So now let's see if life gets better. I think it does. I think this might be the magic bullet here. So I have 2 on the outside. This square root of x, okay, what do I need to get du? I need a 1/2. I need an x to the 1/2 on the bottom, and I need a dx. All of that becomes du. What's left over? I have a square root of x, otherwise known as u, and I have an e to the u. Yeah. We're wizards. Okay, so this is it. And so now this is an easy integration by parts, correct? And I'm out of time. So good for us, we got there. Follow this out, do another integration by parts on that, and it's done. So that's it. That was a good one. I like that one, but that's hard. That's a tricky one to see the substitution that needs to be made for sure. I'm glad you brought that one up. Cool. Thank you, everybody. Have a great weekend. I will see you on Monday.
Thank you.
Are you allowed to ice cream in the store, or is it just coming?
You can go out. That's fine.
Okay.